Hi everyone, and welcome back to the Anime Chem Tutor. In this video, we are going to look at oxidation and reduction and how to calculate the oxidation numbers in different compounds. You may have come across the term redox, but what exactly is that saying? Redox means, or simply redox is an abbreviation for reduction and oxidation, RED from reduction and OX from oxidation. Both oxidation and reduction occurs at the same time. If a substance is being reduced, another substance is being oxidized. So starting off with oxidation. Oxidation can be defined as the loss of electrons. Oxidation can be defined as the gaining of oxygen. Oxidation can also be defined as the loss of hydrogen. And oxidation can also be an increase in the oxidation number of that particular element during a chemical reaction. Now, let us look at reduction. Reduction can be defined as the loss of oxygen. Reduction can be defined as the gaining of hydrogen. Reduction can also be defined as the gaining of electrons. And also, reduction can be defined as a decrease in the oxidation number of that particular element. Now that we understand what redox is in terms of oxidation and reduction, let us look at how to calculate oxidation numbers in different compounds. There are several rules that are used to calculate the oxidation numbers. The first one is the oxidation number of all atoms of an element in the free state is 0. So let us look at an example for that. Aluminum atom, the oxidation for that would be 0 because aluminum is in its free state. It is not reacting or combining with anything. And the same thing for, let's say, hydrogen gas or chlorine gas. So all these elements have an oxidation number of 0. Now look at this next example. You're given the compound calcium chloride, CaCl2, and asked to identify the oxidation numbers of each element within the compound. Because this is an ionic compound, the molecules are split into calcium 2+ and chlorine minus, and so the oxidation number of calcium will match the charge on the calcium ion, and the oxidation number of chlorine will also equal to the charge on the chlorine ion. For simple ionic compounds, the oxidation number is equal to the charge of the ions. Another example is magnesium oxide, which is also an ionic compound and dissociate or split into magnesium 2+ ions and oxygen 2- ions. And if you are asked to identify the oxidation number of each element in magnesium oxide, simply take a look at the charges, and that will equal to the oxidation numbers of the respective elements. So magnesium will be 2+ and oxygen will be 2- in this case. Now for covalent compounds, the oxidation numbers for the elements in such compounds will vary, and so most times you will see the oxidation state of the compound within the name of the compound. For example, iron 2 oxide, which is also a giveaway that iron is in the oxidation state of +2. Another one is potassium permanganate, or it can be read as the manganate 7 ion, which is MnO4-. But how did they arrive at these different oxidation states of the various elements? We will get to that in just a minute. Now, the next rule states that the sum of all oxidation numbers of elements in a compound is 0. For example, iron oxide, which has the formula FeO. The oxidation number of all of both the iron and the oxygen equals to 0. But how do I know that it equals to 0? You know that because there are no charges on the compound. And to understand more about charges and neutral compounds, you can watch my previous video on the formation of ions. Another example is aluminum oxide, Al2O3. Because aluminum forms +3 ions and oxygen O2 minus ions, then that would equal to their respective charges. 2 aluminum times 3, that's +6. 3 oxygen times -2, that's -6. And +6 added to -6 give you a total of 0. The next rule states that the sum of all oxidation numbers of elements in a polyatomic ion is equal to the charge on the ion. So an example of a polyatomic ion is the SO4 2- ions, the SO3 2- ion, the PO4 3- ion, which is the phosphate ion, and so forth. Others are NO3- ions, the nitrate and the nitrite ions. So these are what we call polyatomic because there are more than one atom within the ion and it has a charge. So it's polyatomic ions. And so whatever the charge is on these polyatomic ions, the sum of the oxidation numbers will equal to that charge on the ion. So it's easier to find out the oxidation numbers of the individual atoms or element within those polyatomic ions. Okay, so let us look at some examples. The first example is the dichromate ion. And the question is, what is the oxidation state of chromium in the dichromate ion? The dichromate ion has the formula Cr2O7 2-, and we want to find out what is the oxidation state of the chromium in this particular polyatomic ion. First, we write out the formula Cr2O7 2-, and we put an X under the Cr2 because that is what we want, and it's 2 of them, so it's 2X plus oxygen always have a -2 oxidation state, so it's 7 of them -2 in bracket, close bracket, equal to the overall charge of the ion, which is -2. Now the algebraic equation would be 2x minus 14 equal to -2. Rearranging to find x, we have 2x equal to 14 minus 2, 2x equals to 12, then x equal to +6. So the chromium in dichromate has an oxidation state of +6. Let us look at another example, and this one is iron 3 oxide, Fe2O3, and you're asked to find the oxidation number of the iron in this particular compound. So the first thing we do is to write out the chemical formula of the compound, which is Fe2O3. Then the one that you want to find, you put an X under it. So Fe2O3, put an X underneath, and there are 2 of them, 2 iron. There's a subscript 2 there, so it's 2X plus, and oxygen always have a -2 oxidation number, and it's 3 oxygen. So the 3 times -2, which is the oxidation number of oxygen, equal to 0 because there isn't any charge on this particular compound. And then we have the algebraic equation. We rearrange to find x. So it is 2x minus 6 equal to 0. +3 multiplied by -2, which is in bracket, would give us -6. So now 2x equal to 6. We'll bring over the 6 to the right hand side of the equation, and we divide both sides by 2 to get rid of the 2 on the left hand side. So x equal to 3. So the oxidation number of iron in this case is +3. So no wonder why the compound should be written as Fe3 oxide, to indicate that the iron in this particular instance as a +3 oxidation number. Try this example for yourselves. What is the oxidation number of nitrogen in the nitrate ion, NO3 minus? Okay, so for the NO3 minus, we know that the total charge on this polyatomic ion is -1. So everything on the left hand side will equal to -1. We want to find N, so it's X plus 3 oxygen. We write 3 and oxygen as an oxidation number of -2, so we'll put that in brackets. So it's 3 times the -2 equal to -1. So the overall algebraic equation is X plus 3 open bracket -2 close bracket equal to -1, and so that is X minus 6 equal to -1. Rearrange to make X the subject, so X equal to 6 minus 1, X equal to 5. So the nitrogen in the nitrate ion is as an oxidation number of +5. Let us try another example that doesn't involve oxygen. So in this case, what is the oxidation number of calcium in calcium hydride, that is CaH2? Find the oxidation number of the calcium in that compound. In this case, the calcium we want to know, so first thing we write out the formula CaH2, then put an X underneath the calcium, and because hydrogen is with a metal, it takes on a negative oxidation number, so it is -1 in bracket, and there are 2 of them, so 2 outside of the bracket, and the overall charge is 0. So we have the algebraic equation as X minus 2 equal to 0. Rearrange that to make X the subject. We have X equal to +2. So calcium in calcium hydride has an oxidation number of +2. There are 2 special cases with hydrogen. If hydrogen is with a non-metal, it takes on a positive oxidation number, a +1 oxidation number. If hydrogen is with a metal, then it takes on a negative oxidation number, with the exception of boron. Only with boron, hydrogen will have a +1 oxidation number. Let us look at another example. You are given the reaction zinc plus sulfuric acid give zinc sulfate and hydrogen gas, and you are asked to determine the oxidizing agent and the reducing agent in this reaction. Now, the oxidizing agent causes something else to be oxidized while it itself is being reduced, and the reducing agent causes another species to become reduced while it itself is being oxidized. So oxidizing agents undergo reduction and reducing agents undergo oxidation. Now, in the reaction that was given, first we need to identify if it is balanced, and it is. Then we need to work out the oxidation number for each species to determine which is being oxidized and which is being reduced. So for the zinc, because it is elemental, it is a neutral atom, it has an oxidation number of 0. So now let us work out the oxidation number of zinc in zinc sulfate. The zinc in zinc sulfate has an oxidation number of +2. Why? Because sulfate ion is 2-, and because it is a neutral compound, then the 2- must be cancelled out by a +2. So that is how we can easily determine the oxidation number of zinc in that case. So zinc is moving from 0 to +2. So that is an increase in oxidation number. So zinc is being oxidized by the sulfuric acid. The hydrogen in sulfuric acid, it has an oxidation number of +1. And over on the right hand side, where we have hydrogen gas, because hydrogen gas is a neutral molecule, it has an oxidation number of 0. So hydrogen is moving from +1 to 0. So that is a decrease in oxidation number. so hydrogen is being reduced by the zinc. So let us sum up what we have now. Sulfuric acid is the oxidizing agent. Zinc is the reducing agent. Zinc was oxidized by sulfuric acid. Zinc in return caused hydrogen to be reduced. Now let's write the oxidation and reduction equations for the reaction. First, you have zinc solid lost 2 electrons, so that's minus 2 electrons, to produce zinc 2 plus. Checking to see if the equation is balanced. So we have one species of zinc over the left hand side and the same amount over the right hand side, so that equation is balanced. Then for the reduction, we have hydrogen gained 2 electrons to give hydrogen gas. Checking to balance the equation. So hydrogen gas, so we have 2 hydrogens over the right hand side, so we must put a 2 beside the hydrogen over the left hand side, and so the equation is balanced. So both the oxidation and reduction equations look like this for that reaction. Notice that the sulfate ions remain unchanged throughout the reaction, and so it can be ignored. And species like these are called spectators. This is where we stop for today. Thank you for watching and see you soon.